All right, so this is problem set 3-4b. So question 1 gives us functions, and we're trying to find the open intervals of up or down concavity. That's going to require us to find the second derivative. Let's do the first function, which is negative x cubed plus 6x squared minus 5. And so if we take the first derivative, it's going to give us negative 3x squared plus 12x. And then we're interested in the second derivative, right? So that's negative 6x plus 12. And so where's this going to equal 0? Second derivative equals 0 when x equals 2, right? So that's going to split our number line into two potential intervals. And so for negative infinity to 2, right, the first interval, what we are going to have is we want to test whether this second derivative is positive or negative within this interval. So we're going to test a certain point. We can maybe test x equals 0. And that means the second derivative will be 12, right? And so that means this interval is concave up. So we have plus here. And for the other interval, we could maybe test x equals 3, and we'll find that the second derivative is equal to negative 6. So that's concave down on that interval. So we'll have a minus here. Okay, so that tells us that x equals 2 is a point of inflection. That's because it goes from plus to minus in terms of concavity, and the function is also defined at that point. We don't have an asymptote or anything like that. Let's do the next one. Here we have a quartic 4 minus x minus 3x to the fourth. So if we take the first derivative, we're going to have negative 1 minus 12x cubed. Second derivative is going to be negative 36x squared. Okay? Is that right? I think so. And so the second derivative will equal 0 when x equals 0. So we really only have two intervals here. So from negative infinity to 0, we can test x equals negative 1, f double prime of negative 1 is going to be negative 36. So that means that this is concave down. For the other interval, 0 to infinity, we can test x equals 1. This is also negative 36, so it is also concave down. Okay? And so it looks like the second derivative is negative for the interval negative infinity to 0, and then it briefly becomes 0 when x equals 0, and then it goes back to being negative at the other interval. So what that tells us is that even though the second derivative is equal to 0 when x equals 0 is not actually a point of inflection, because the second derivative doesn't change. So the function doesn't change concavity. No points of inflection. Okay, if you graphed this, you would also see that. Let me confirm that on the graph. Yeah. It's actually a very interesting graph if you look at it. Okay, next one. Question C. f of x equals x times the square root of x plus 3. Take the first derivative, we're going to have to use product rule. You can maybe rewrite this as x times x plus 3 to the 1/2. If we do product rule, we're going to be left with x plus 3 to the 1/2 plus x times 1/2 times x plus 3 to the negative 1/2. I think that's correct. Simplify this a little bit. Now if we take the second derivative, we're going to have 1/2 times x plus 3 to the negative 1/2. That's chain rule. Then we have to do product rule again, taking the derivative of this other thing. We're going to be left with, this one's not so easy, is it? Okay, so if we combine all these terms, we're going to have x plus 3 to the negative 1/2 minus 1/4 x plus 3 to the negative 3/2. Okay, so we're going to want to factor this, and this might be tricky for some of you guys. The next step that we want to do is actually to factor out an x plus 3 to the power of negative 3/2. Okay. And when we factored that from this first term, we're going to be left with x plus 3. It might be a little tricky, so make sure you understand why that is. Therefore, we're going to be left with 3/4 x plus 3 over x plus 3 to the 3/2. Okay. If I simplify that a little more, be left with 3 x plus 4 over 4 x plus 3 to the 3/2. All right. Just use a computer to check that this is correct. Looks good. Okay. So, for this second derivative, let's identify all those quote-unquote critical points. So one point that we'll care about is x equals negative 4, because x equals negative 4, actually this is quite tricky. First of all, we have to think about the domain, okay? So actually this function is not defined for all real numbers. Okay, note that f of x is only defined for -3, infinity. because when we go back to our original function, this function is clearly only possible if x plus 3 is a positive number, or a non-negative number. And so that tells us that we're actually restricted to this interval. So actually we really only care about that interval. And if we look at the numerator, x equals -4 is not even within this interval. And so we don't even need to care about that number. And if we think only within this interval, actually we would see that this second derivative never equals 0. It never equals 0, and it's never undefined. And so there's only one interval that we need to check the concavity for, and that is -3, infinity. And so for this, we can just test one number. We can just test maybe, I don't know, x equals -2, let's say. And so f double prime of -2, we'll just plug it into here. F double prime of -2 will equal 3 times 2 over 4 times 1. That's 3/2. That's a positive number, right? And so this will be concave up on this interval. And because the concavity never changes sign, there are going to be no points of inflection. Check that with my calculator. Yep, always concave up. All right, let's go on to question 2. Here we're trying to find the extrema using the second derivative test. Okay, so remember, what's the second derivative test? In order for a critical point to be a relative minimum, first we have to have, right, if this is our relative minimum here, first we have to have the first derivative equal 0, and secondly, we also have to have the second derivative to be greater than 0, because that will give us a function that's concave up. So that will give us a relative minimum. All right, so we would just calculate the critical points using the first derivative, and then plug that critical point into the second derivative and check whether it's positive or negative. If it's negative, then we'll have a relative maximum. Okay, so every time you think about this second derivative test, always draw it out, and so that way you don't confuse yourself. So think about a minimum is always a dip, and so that always has to be concave up. Let's do it. Question A, f of x equals 6x minus x squared. So the first derivative will be 6 minus 2x, and the second derivative is actually just -2. All right, so what is the critical point? The critical number is going to be x equals 3. And so, is that going to be a maximum or a minimum? Well, we can just check. Is f double prime of 3 negative or positive? Well, it's -2, isn't it? Actually, the second derivative never even changes. It's always concave down. And so that tells us that x equals -3 is a relative maximum, because the second derivative at that critical number is negative, so it has to be concave down, which means that the top is a maximum. Question B, f of x equals x to the 4th minus 4x cubed plus 2. So here, the first derivative is equal to 4x cubed minus 12x squared. X cubed minus 12x squared. And the second derivative is equal to 12x squared minus 24x. I think that's correct. Okay, so what are the critical points going to be? Let's calculate the critical points. So the first derivative is going to equal 0. We are going to have to factor this, aren't we? So the two critical points are going to be x equals 0 and x equals 3. So those are the potential maximums and minimums. So what is f double prime of 0? The second derivative at x equals 0 is just 0. And so that's inconclusive. Right? In order for the second derivative test to work, it either has to be positive or negative. If it's 0, that doesn't tell us anything. If we plug in the second critical point, x equals 3, the second derivative will equal 108 minus 72, which is 36. So that tells us that x equals 3 is a relative minimum. Okay? Normally, if you were really trying to find whether x equals 0 is a maximum or minimum, you would actually have to apply the first derivative test. But since that is not really the aim of the question, I will not require that. Okay, remember the first derivative test, we find the open intervals upon which it's increasing or decreasing. So here we have these three intervals. And I think if we calculated those intervals, we would find that this is minus as well, and then this is plus. Okay, so only x equals 3 is a minimum. X equals 0 is actually neither a maximum nor a minimum because it doesn't change sign. So the graph actually would look like this. Okay, something like that. You can check with a calculator. Part C, f of x equals x plus 4 over x. I'll just specify this. So the first derivative will be 1 minus 4 over x squared. I feel like we've done this question so many times. I don't know why. And then the second derivative is going to be 8 over x cubed. Is that correct? Wasn't this on the classwork? Oh, it was on the classwork. Oops. Well, still have to do it. Is this correct? Yeah, should be correct. Okay, so the first derivative we can simplify a little more as x squared minus 4 over x squared, which factors as x minus 2 times x plus 2 over x squared. All right, and so the critical numbers, right, that's where the first derivative is 0, are going to be x equals negative 2, 0, and 2. Now the second derivative at negative 2 is negative 1. The second derivative of 0 is undefined. And the second derivative at 2 is going to be 1. So that tells us that x equals negative 2 is a relative maximum because the second derivative is negative. And x equals 2 is a relative minimum. And that finishes up my lecture. Sorry, not lecture, solutions.